So good morning students, welcome back. Today we are going to discuss Ampere circuital law, okay, and its first application. So let's start with Ampere circuital law. So we'll start with Ampere's circuital law. Okay, so first of all I'm going to tell you the meaning of this law. Okay, where is it applicable? Okay, the basic thing is it is applicable when current flows in closed loop. When current flows in closed loop, that is an important portion. Whenever the current flows in a closed wire, in a closed circuit, in a closed loop, in that condition, we will apply Ampere circuital law. Okay, so whenever the current flows in partial length, that is a small segment, that is taken as DL. That is a small segment, small portion. When current flows in a small portion in a loop, in a conductor loop, in that condition, it produces magnetic field. How much magnetic field is generated by? That is explained by Ampere's. It states that closed integration of magnetic field is always equals to mu naught times of total current. Look at students, what is the meaning of this mathematical terms? Look at the linear, this is small segment, the linear closed integration of magnetic field. Okay, about this circuit, this is a closed loop. When current flows in a partial length of closed loop, it produces magnetic field, and linear closed integration of that magnetic field is always equals to mu naught times of total current of that circuit. It is explained by Ampere. Sigma I is total current of that circuit. Mu naught, that is called permeability. That is called permeability of free space. Okay. B is the magnetic field. DL is a small segment, and I, sigma I is the total current. So what will be the statement? See one more time. The linear closed integration of magnetic field always equals to mu naught times of total current of that circuit. This is the mathematical form of Ampere circuital law and statement. Its first application, we are having generally three applications. Our first application is find magnetic field due to infinite long current carrying conductor. Second application will be find magnetic field due to solenoid. Okay, and third will be find magnetic field by toroid. So first we'll discuss the first application, find magnetic field due to long infinite straight current carrying conductor. Okay, so let's start. Look students, our first application of Ampere circuit law is our first application. Okay, find magnetic field, okay, due to infinite current carrying conductor. Okay, so first of all I'm going to tell you, find magnetic field due to infinite current carrying conductor. Okay, now students, this is a XY, that is the wire. It is not possible to take a infinite long wire, so we'll take it small segment. Let XY is a small segment of infinite long straight current carrying conductor. Okay, and it's having some current I. We know Ampere circuital law is only applicable when current flows in closed loop. The current is open now, we can't apply Ampere circuital law. In order to apply Ampere circuital law, we have to take a closed loop. So what we'll do, students, we'll assume a circular closed loop, and this circular closed loop is said to be Amperian surface. It is said to be Amperian surface of radius A. Now we can take a particular point P. Okay, and this will be taken as a partial segment. At P point we'll find magnetic field. Okay, and this is small segment DL. So when current flows, it produces magnetic field at particular point P at the distance A. This closed surface is called Amperian surface. Now current comes in closed surface. Whenever the current comes in closed surface, we can apply Ampere circuital law. So now I'm going to apply Ampere circuital law. the linear closed integration of magnetic field is always equals to mu naught times of total current. B dot dl equals to mu naught sigma I. Whenever you remove dot, there always come cos theta. BDL cos theta mu naught sigma I. Okay. Now students, the theta, we know students the small segment having the direction outward perpendicular, and look at, and magnetic field are also in same direction. Okay, for particular point P, dV and dl are in same direction. dV means magnetic field B, and partial length are in same direction. If two components are in same direction, theta as taken as 0 and cos 0 will be 1. What is the reason behind it? B and dl are in same direction. Okay, so cos 0 is 1, so only remains BDL mu naught sigma I. Now students, B comes outside from integration because magnetic field is a constant quantity. It comes outside, and integration dl and mu naught sigma I. Look students, you can take a screenshot of this portion because I am removing the upper portion. Okay, now see. Look students, simple thing. Integration dl means total length of Ampere surface, that is the circumference. So that will be what? 2 pi a, and sigma I is the total current of that closed circuit, that is I. So sigma I replaces as I. So we have to find magnetic field B mu naught I upon 2 pi a. So how much magnetic field generated by infinite long straight current carrying conductor? That will be mu naught I upon 2 pi a. This is the magnetic field generated by an infinite long straight current carrying conductor, and this was the first application of Ampere circuital law. Okay students, understood? Now we'll start the second application, one of the most important application, find magnetic field due to solenoid. So first of all, I'm going to explain what is the meaning of solenoid. Now students, solenoid, a long cylindrical shell, a long insulated cylindrical shell on which copper wire wound in helical form. Okay, a long insulated cylindrical shell on which when we wound copper wire, on passing current it produces magnetic field, it behaves like a magnet. Such device is said to be solenoid. What is the use of solenoid? Solenoid actually is a types of electromagnet. Solenoid is a types of electromagnet. And what is the purpose to make the solenoid? Its main purpose for making the solenoid is to produce controlled magnetic field. It is used in lots of devices. And it produces controlled magnetic field along like this, a long insulated cylindrical shell on which when we wound copper wire in helical form, on passing current it behaves like a magnet, it produces magnetic field, controlled magnetic field. Such device is said to be solenoid. So now using Ampere circuital law, we have to find its magnetic field generated by a solenoid. So in which we can find, look at students, for that I want to make the diagram. Look at students, suppose this is the solenoid, okay, and this is the wire. When we pass current through it, it produces magnetic field. L is the length of the solenoid, okay, and small n is the number of turns in per unit length. Okay, students, the main thing, current is flowing from one end and is releasing from other end. So it is not closed current. Current is not flowing in a closed loop. We know Ampere circuital law is always applicable when current flows in a closed loop. So what to do? In order to applying Ampere circuital law for making closed loop, we will assume a closed surface. Look at students. This is the closed surface that I assume in solenoid. Give the name as P, Q, R, S. Okay, so current also flows in that closed loop due to wire. When it comes in contact with wire, it also having some current, and now current is flowing in closed surface. Look at students, now current is, and its length is dl, its partial length is dl of this surface. This is called Amperian surface. I assume a closed surface in solenoid having length partial and dl, and it having some current I. Now current is flowing in a closed loop. Now I can apply Ampere circuital law. Okay, so what is Ampere circuital law? Closed integration of B dot dl equals to mu naught sigma I. Students, this PQRS, closed Amperian surface, okay, made by 4 wires, PQ, QR, RS and SP. So it produces all that small segment, all that individual segment will produce magnetic field. PQ wire will produce magnetic field, QR, RS, SP. All the side will generate magnetic field. So I'm going to break this B dot dl in 4 parts. Why? Because all the individual wire will produce magnetic field. So I'm going to write here B dot dl, closed integration of B dot dl plus closed integration of B dot dl, closed integration of B dot dl, mu naught sigma I. Now I'm going to clear you this BDL produced by PQ wire. So I can write here from P to Q, and this is for Q to R, R to S and S to P. Okay. Now students, whenever we remove dot, there comes cos theta. So in that 4 we write BDL cos theta, BDL cos theta, BDL cos theta and BDL cos theta equals to mu naught sigma I. Students, for this is for P to Q, Q to R, R to S and S to P. Now the important thing, look at students, this will be the magnetic field line. Okay, just we'll assume P to Q. Look at the first, second, third and fourth. Look at the first, consider on first and third. Okay, so we'll start with first P to Q. P to Q. P to Q is parallel to the field line. Look at this is a field line. This PQ wire is parallel to the field line. So in the first, when 2 components are in same direction or parallel, theta is taken as 0 degree. Here I am going to take 0 degree. What is the reason behind it? Because PQ is parallel to the field line. So theta is 0. Now come on that second component, QR, Q to R. This is the DL and this is the field line. These are perpendicular. So cos will be what? 90. Okay. Come on the third portion, BDL cos theta, third port R to S. In that condition, in R to S, this portion is situated outside the solenoid. Okay, students, look at RS portion is situated outside the solenoid. This is R solenoid. So this is the outside the solenoid. There will be no magnetic field. This component will not generate any magnetic field. Why? Because that is situated outside the solenoid. So here I am going to write outside the solenoid. So it will be 0. Okay, there will be no magnetic field. It will not participate in giving the magnetic field. Why? Because this is outside the solenoid. And finally, P to S. That is, this wire again is perpendicular to the magnetic field line. For perpendicular line, cos 90. Look at students. Cos 90 is 0. This portion becomes 0. Cos 90, this portion also becomes 0. Cos 90, it becomes 0. That is outside, again 0. Only the single component, this PQ wire, will give the resultant magnetic field. So now you can take a screenshot, students. I am going to remove upper portion. So what will write, students? Look at this first portion. Only the first P to Q, BDL cos 0. I am going to write and mu naught sigma I. Okay students, now finally cos 0 is 1 and b comes outside from integration dl, and here we are having mu naught sigma I. What is mu naught sigma I? Total current of this square loop, that is NIA, that is NIL, nil. How students? Actually sigma I means total current, and here total current is given by NIL. Current in, it means NIL means what? Total current of N turns and L length of wire of this closed loop. Okay, N is number of turns per unit length, I is current, L length. NIL means what? Total current of N turns and L length of the solenoid. And here integration DL means total length, that is L. Total length of the solenoid is what? L. So finally instead DL will write L and mu naught NIL. Now students, L to L cancel out. L to L cancel out. Okay. And this side we are having only B and mu naught Ni. So we got the magnetic field of solenoid. How much magnetic field generated by a solenoid? B equals to mu naught Ni, where mu naught is permeability and small n, number of turns per unit length, and I, total current. One more thing I want to explain. Students, small n. How can you find number of turns per unit length? Number of turns per unit length, that we'll find by N by L, total turns by total length. So small n can be replaced by capital N by L, where capital N is what? Total turns. What is the major difference between small n and capital N? Small n number of turns in per unit length, and capital N is total turns. Total turns by length is said to be number of turns in per unit length. So finally we can get one more form of magnetic field of solenoid. B equals to mu naught Ni, either mu naught capital N I upon L. Equation suppose first and this will be second. So we got the two forms, mu naught Ni and mu naught Ni upon L. Small n total capital N. Small n number of turns per unit length, capital N total turns, and that is the relation. Total turns by length is called number of turns per unit length. Finally we discuss the last application, toroid. What is toroid? Actually when we bend a solenoid in circular form, that is called toroid. Actually a endless solenoid is called toroid. Look at students, when we bend a solenoid in the circular form, this will be the number of turns, that is the copper wire. Okay, when you flow current, obviously it produce magnetic field. Okay, at the center the radius is R and it produces the magnetic field particular dB. Suppose it produces magnetic field dB, and this will be the, suppose, small segment taken as dl. Solenoid will generate both types of magnetic field. Okay, cross means perpendicular downwards, and then after dot means magnetic field perpendicular upwards. It produces both types of magnetic field. So when we bend a solenoid in circular form, okay, that is called toroid. It also produces the magnetic field, control magnetic field. Okay, it actually toroid is an endless solenoid. It is used in, I will give example. In that fan, in ceiling fan, we use that motor, circular motor, that is a toroid. In the engine of scooty and bike, we use that coil, that is also example of toroid. Okay, that generate magnetic field. So now we have to find the magnetic field of toroid. How can you find, students? Look at, current is flowing. Actually toroid itself a closed surface. In first application, second application, in a straight wire, in solenoid we assume a closed surface, Ampere surface. But here we don't require to assume circular closed loop because toroid itself a closed surface. So when the current flows in a closed surface, it produces magnetic field. Ampere circuit law is applicable, and that is B dot dl equals to mu naught sigma I. When you remove dot, there come cos theta, B dl cos theta, mu naught sigma I. Look at students, here the direction of this segment is outward perpendicular. Okay, B and dl are in same direction for circular device, and for circular object always two components are in same direction. B and dl are in same direction, so theta is taken as 0 and cos 0 is 1, and here sigma I means total current Ni and total turns I current. Sigma I means total current of all the turns. Actually current for 1 turns is I and current for n turns is Ni. So Ni will be what? Total current of this toroid for n turns. In that first equation I will make two change. B comes outside, integration dl will remain, cos 0 will be 1 and mu naught sigma I become Ni. Now students, integration dl means total length of this toroid, that is of radius r, that will be a circumference 2 pi r. So B equals to, that is 2 pi r mu naught Ni. Now students, you can take a screenshot. I am going to remove the upper portion. Have you understood? I think. Now students, we have to find B, magnetic field. There comes mu naught Ni upon 2 pi r. So we got the first form. How much magnetic field generated by toroid? Mu naught Ni upon 2r. Mu naught is permeability and total turns I current, r is the radius of toroid. Now students, we can take one more change in that, and total turns 2 pi r total length, n upon 2 pi r become small n. It means number of turns per unit length. Okay students, total turns by length. Actually n is total turns and 2 pi r total length of the toroid. Total turns by total turns, total turns by total length is called small n, number of turns per unit length here. So this term we can written as B equals to mu naught Ni. So this will be the magnetic field of a toroid. It is similar to solenoid, but one major difference is there. In solenoid, small n means what? Capital N by L in case of solenoid, and in case of toroid, small n means what? N upon 2 pi r. That is a major difference. Okay students?